So let's look at stochastic input to linear systems. We could also look at stochastic input to nonlinear systems, but this is a special case. So this is with, later we want, being electrical engineers, we want to put a receiver design as a signal with the signal plus noise comes in. So we want to do the receiver design, etc. So with that in mind, let's look at the general problem. You have a stochastic process x of t. Remember, it's various realizations, right? With some mean and autocorrelation function. By this I mean, we know everything about the input. We know its mean is given, autocorrelation function is given. We pass it through a system. So y of t is L of x of t, a linear system. And we want to find out the mean, autocorrelation, and the cross correlation function, etc. I'll explain to you what the cross correlation is. But very quickly, what is linear system? So linear system means if you have an input which is, let's say xi of t, the system produces the output to yi of t, right? In other words, if I put one process x1 of t, I get y1 of t. x2 of t, I get y2 of t. Then if I take a linear combination and apply it to the system, a1 x1 of t plus a2 x2 of t, what do you get? Anybody? Oh, that's the whole point of a linear system. It will be a1 y1 plus a2 y2. And so I also want to look at time-invariant systems. So that's called LTI. So time-invariant system means that if x of t produces an output y of t, and if you come and do the same experiment tomorrow morning, what will happen? What will the system produce? Alright, so that's the whole point. You get the output also gets translated by the same amount. So remember, so if the input is like this and you get an output like this, and if the input is shifted, this output also is shifted. That's what, right? That's what we mean by, so if this shift is t naught, here also you get the same output. Of course, if the system is not time invariant, you are going to get a completely different output. We want to consider systems which are both linear and time invariant. So the whole point is such systems has its own, can be characterized by its impulse response, right? So I think the proof goes something like this. So we want to find out y of t So y of t is L of x of t. So x of t, I am going to write it as, to make use of these properties, suppose I write this as right? This is certainly true, right? X of t using a delta function. So let me plug this in here. So this is L of integral x of tau delta of t minus tau d tau. Now look here, linearity, you think of the integration as summation. Look at here. That means if you have an integral inside, it's the sum of the terms. So the integral goes outside, right? So I can write from here y of t as, another way is you write this as summation, you approximate it, because this expression you can write it as ai of delta t minus tau y, etc. Where ai would be this x of tau y, x of tau y multiplied by delta I. And then this will be, the L will go and sit here, right? So this is the same as L applied to this. That's the whole point of linearity, right? And then you, so integration, summation becomes integration. Ai's are x of tau, then L applied to this is the same as, so I'm going to call L of delta t to be some function h of t. Then this is h of t minus tau y, so you should see, you get this familiar expression. You see what I did? So suppose I call the system acting on an impulse. So system is here, system is a black box. I hit it with an impulse, delta of t, and of course something will come out. Impulse is not going to come out depending on the system. Whatever is going to come out, I'm going to call it h of tau. So this is the impulse response of the system, right? This is characteristic to the system. It has nothing to do with the input anything. This is just an impulse response, literally. That's like the signature of the system. So what I have shown you, this is just a classic elementary, if you apply now the system to any input x of t, then the corresponding output is, you have seen this, right? X of tau, h of t minus tau d tau. What do you call this operation? Anybody? This is convolution, right? X of t convolved with h of t. So you have a minor theorem here. If a linear time invariant system is hit with an arbitrary impulse, arbitrary signal x of t, the output is x of t convolved with its signature, which is h of t. Interesting thing is this h of t is only depends on the system parameters and features. All right, so what? Now we want to apply this theory to see how to compute the mean and variance of the output. Output is already here, look at here. So if this is a stochastic process, for every realization, you put the realization, take the convolution. So I'm going to get a different realization. So it's very easy to see that a stochastic process generates another stochastic process here. So the question is, what is the mean of the output? So this I'm going to write mu y. It could be a function of time, we will see. So what's the definition of this? This is expected value of, look here, x of tau, h of, yeah, or either way, either you can also write it the other way, by the way. X of t minus tau, h of tau, d tau. Just make a change of variable here. So expectation and is a linear operation, as I showed you here. So this goes, you can write this as integral expected value of x of t minus tau, h of tau, d tau. Oh, but look at here, what is this? This is mu of? Huh? Yeah, mu of t minus tau multiplied by h of tau d tau. So what's that expression? Anybody? Look, this is exactly looks like this. So this is the convolution between mean and the impulse response. So you can say look at here, the output autocorrelation function is the input autocorrelation function convolved with, so if you want, you can write this as input autocorrelation convolved with h of t. This is the output autocorrelation. So if the input is not Whiteson stationary, the output doesn't have to be Whiteson stationary, because this will be a function of t. Look here, hello, right? If this is a function of t, that will be a function of t also. But we will of course come to that, but you can see it all. Suppose the input had a constant mean, then what happens? Input had constant mean, this would be a constant, then that goes outside. This will be a function, that will be a constant. So you already see that, right? Input constant, so I'll write it here. If x of t, x mu of t is a constant, then output is simply another constant, because it is mu x multiplied by So if x of t is Whiteson stationary, at least the first part is true, the first part is true here also, right? So let's look at the cross correlation function. Look here. What is it you are going, somebody had an issue? I'm going to come to that. So let's look at, so why I call this cross is because, look here, it is natural. Hello, you have input and output, so why not look at the cross correlation function? Then we will look at the output. So this is the cross correlation function. So again, you will see the reason for this. So I'm assuming that we could have complex processes. So this is by definition expected value of xt1. Then you see yt2. Yt2 is, y definition is here. So I'm going to put here, so this of course I can write it like this, or I can write this as, so let me put a t2 here. Then this will be t2, etc. So this will be integral x of t2 minus alpha h alpha d alpha, but with a star, right? Because of this star. So I pull out the integral outside, then I have expected value of xt1 x star t2 minus a tau or alpha h star alpha d alpha. So of course this is integral rxx, what is it, t1 comma? This one, right? So t2 minus alpha, then h star of alpha d alpha. So you see this is the convolution on the second variable. So if you want, you can write this as rxx t1 comma t2 convolution on h star of t2. Because this dummy variable tau is on the second variable. So that's the answer. The cross correlation, look at the cross correlation function is given in terms of the autocorrelation function. So what is the theorem? That's a minor result. If a stochastic process is applied to a linear type invariant system, its autocorrelation function, its cross correlation function is the autocorrelation function convolved with the system impulse response on the second variable. And you have to take care of the complex conjugation also. All right, so now, so I'm going to call this the second result. The first result is here, right? This is 1. This is a byproduct of 1. So I'm going to call this 1a. That's 2. Now you wanted the the autocorrelation function of the output. So let's look at ryy t1 comma t2. That's by definition expected value of yt1 yt2 star, but yt1 is expected value of x of t1 minus beta h beta d beta. So look at here, for yt1 I substituted this, right, because here yt1 here. So yt1 would be, look at here, yt1 would be x of t minus a dummy variable beta, h beta d beta, which is what I have written there. Now let me take the integral outside, then I have expected value of x of t1 minus beta. Then you see I have y of T2 star. Of course, if I want, I can expand it. I don't need to. H beta D beta. Now, you know this term. Look at here. That looks like this. Where? Here. X and Y. So this is the cross correlation function, isn't it? So I can write this as integral Rxy. Look at here. Rxy T1 minus beta comma T2. So T1 minus beta comma T2 H of beta D beta. What is this? Anybody in terms of convolution? It is convolution on the first variable, right? So if you want, I can also write this as Rxy T1 comma T2 convolved with H of T1. But you see, you already have an expression for this. Rxy is somewhere here. Here. This is Rxy, right? Rxy T1 comma T2 is Rxx. So if I substitute it here, you also get what I did was I substituted for Rxy T1 comma T2 as Rxx T1 T2 H star of T2 convolved with H star H of T1. Convolution is linear operation, so it doesn't matter where I put it up. So this is the output cross correlation in terms of the input, output autocorrelation in terms of the input autocorrelation and the system impulse responses. So we answered these questions here. So let me write down the answer here. So the question was, what is the mean of the output process? Anybody? Mean is what? Input mean? Convolved with H of T. So how about the cross correlation function? Anyone? Rxy. So this is Rxx T1 T2 convolved with H star of T2, right?
Yeah, H star.
And finally, Ryy T1 comma T2, we have two expressions. We can write it in terms of Rxy T1 T2, which is the previous line, convolved with HT1, right? Or you plug this in, you also get this to be Rxx T1 comma T2 convolved with H of T1 convolved with H star of T2. Okay, so in general, of course, if this is not Whiteson stationary, the output is not Whiteson stationary. But now let's ask the question, what if the input is Whiteson stationary? So that's what I'm going to do it there. So let's say, suppose the input is Whiteson stationary. Actually, we already did it here. Look, the first part is easy. If the input is Whiteson stationary, its mean is a constant. Then what about the output mean? All right, so I'm just going to copy that result. The output mean is input mean, which is constant. Here two conditions you have. Mu x is a constant. Rxx depends only on T1 minus T2. Okay. This is what we are starting with. So this convolved with H of tau, which means mu x, I just went through this, mu x H of tau d tau. So that's another constant. So this is a constant. So the mean of y of t is a constant, right? So let's look at R x y t1 comma. Let's see what happens to the cross correlation function. It's somewhere here. We don't have to write anything. Look here. So this is equal to this. So just to follow me, all this is still true. But when you come here, this is still true. When you come to the last line, we can make use of the Whiteson stationarity property. What is the property here? Anybody? Look here. If x of t is Whiteson stationary, you can rewrite this as what? T1, right. So this is going to be T1 minus the second variable, right? So let me, I'm copying this line with saying T1 minus T2 plus alpha. So this is going to be Rxx T1 minus T2 plus alpha H star alpha d alpha. So let me call T1 minus T2 to be tau. This is a standard notation. So what you see there, if you, maybe you are familiar, maybe you are not. So if you convolve Rxx tau convolve with h of minus tau, remember if you convolve it with h of tau, you would get minus here. So let me convolve with two functions. Let's say g of tau and h of minus tau. Let's see what happens. So this is you can definitely write this as h of minus or let's see. Or let me try tau itself. So this is h of minus alpha, g of isn't it right? First, I take this as the first function as it is. Here you replace it by t minus tau or tau minus alpha d alpha, right? Right? Now instead of minus alpha, you put a beta. So this will become h of beta. I mean, if I had a star here, I have a star here. So minus alpha is beta. So this is g of tau plus beta d beta. If this is minus infinity to plus infinity, this will flip again and you'll get the same limits. So which is what we have here, right? Tau plus alpha, h alpha, d alpha. Of course, I can write it like this. Okay? So whenever you see plus here, it's going to be the convolution with a minus sign here. So what does that mean? Anyone? So at least we can say that x of t and y of t are what? So this is you can introduce this new concept. What would you say? Look, the cross correlation function depends only on, tau is what? Tau is actually t1 minus t2. So the cross correlation function depends only on t1 minus t2. So if you can say, if you want, you can say x and y, x of t and y of t are jointly Whiteson stationary. That's what we mean by. Now finally, let's do RYY tau, t1 comma t2. Look here, it's already, the expression is somewhere here. So we can, let's analyze this. We start from here. And this is the same as here. So you went through this. So this is still true, t1 minus beta comma t2. This is Rxy. But we just concluded that x and y are what? What did we conclude here? Look at what is written. Rxy t1 comma t2 is the same as, you can, it's only a function of, so from here we already have that Rxy only depends on t1 minus t2 from here, right? So what about here? Rxy, Ryy here. Ryy here is the same as Rxy t1 comma t2. So this is going to be, because we have already concluded x and y are jointly Whiteson stationary, this could be written as minus, right? So this will become t1 minus t2 minus beta. So let me just write it there. Oh, so this will become Rxy t1 minus t2 minus beta. Then what? Look at here. H beta d beta. So what is this expression? Anyone? Of what? T1 minus T2 I'm going to call tau. So tau convolved with H beta? It's not H beta, look at here. But the beta is a dummy variable tau. Why I had minus here is because of this. If this was minus alpha, this would be not heavy here, right? I just went through all this stuff. So you have some work to go home and redo all this stuff. So look here. So I don't have to write this anymore, T1 comma T2. So I should be able to write now like this. So isn't this right? Rxy tau. So these are the relations now. I'm just writing what we had before. Rxy tau is Rxx tau convolved with H star of minus tau. And Ryy tau is Rxy tau convolved with H of tau. And if you want to substitute this result here, you can also write this as Rxx tau convolved with H of tau convolved with H star of minus tau. So what is the conclusion? If x of t is Whiteson stationary, what do you conclude? Y of t is? So the bottom line is y of t is also Whiteson stationary. So let me just state the theorem once more and stop it. You have a linear time invariant system. The input is Whiteson stationary. What we just showed is the output is also Whiteson stationary. So if the input is not Whiteson stationary, what can you say about the output? In general, not Whiteson stationary. But there may be exceptions. So let me just show you that one good exception, right? So for example, I think let's look at the differential operator. So any questions? Right? So if this is Whiteson stationary, what can you conclude about output? This is Whiteson stationary then? Yeah, for the same reason, linear time invariant system, Whiteson stationary, Whiteson stationary. But in general, of course, this is not Whiteson stationary. You'll have to work out that stuff, right? So what is mu x prime of t? Anybody? We just concluded. Hello, something is bothering you there? Is there anything you want me to explain? Everything is clear? So remember, the output autocorrelation is input autocorrelation convolved with h of t convolved with h star of minus tau. The cross correlation is of course x of t convolved with h star of minus tau. And the mean is what? How do you get the output mean from the input mean? Anybody? You remember the expression? I had it before. What was it? Yeah, so if you have the mean of x of t, the output mean is the convolution of the, right? System applied to the input mean. So if you apply this system, don't you see it? This is the same as, right? That's what it is, right? This output is the same as mu x of t convolved with h of tau, which I can write it like this also, right? The system This is the same as L applied to mu x of t. So if you want a diagram, you can also write it like this, right? Rxx t1 comma t2 applied to h star of t2 gives you Rxy t1 comma t2 applied to h of t1, it gives you Ryy. And in the Whiteson stationary case, you have right, Rxy tau is Rxx tau convolved with h star of minus tau. Then this convolved with h of tau gives us Ryy tau. Where am I getting all this? From these expressions, right? I'm just putting this into symbolic. Then we can solve that problem very quickly from here, right? So from here, the output mean is input mean applied to the system. Of course, the input mean is, if the input process is Whiteson stationary, what would be the output mean? All right. This will be what? Look at this. This is Rxy. Look at here. Rxy t1 comma t2 you can obtain by applying the system to the second variable, right? So that would be, you should be able to see that that's the same as right? Hello? What do you mean by applying the system to this variable? System is derivative with respect to t2, right? And similarly here, look at here. If you want the output autocorrelation function, which is x prime, this you apply to the system, which is a differential with respect to the first variable, right? So you also get so in general, you can write it like this, right? So we already concluded this, right? Because it's a linear time invariant system. So that's done. Now, if you want a problem, let's take x of t to be a Poisson process with the parameter lambda t. Anybody remembers it's a mean? Mean of x of t is what? We did this last class, right? Okay, very good. And what's the autocorrelation function? T1 minimum of T1 comma T2, right? Which is the same as all right, now what? Now I want to pass this through a differentiator. Let me call the output to be y of t. So let's quickly do it. So if this is what I'm asking. If you pass the Poisson process through a differentiator, you get some process at the output. For now, let's call it y of t. I'm just interested in its mean. The Poisson process, is it Whiteson stationary or not? No. So let's look at the output process. What is its mean? Anybody? You can use this expression, right? Just an application here. Hello. This is given. So this is lambda t. Derivative is what? So that's a constant, right? Let's look at the cross correlation function. What do I have to do? Anyone? Look at the expression there. Cross correlation function is given here. So let's differentiate this with respect to T2. What do you get? First line. Plus. See, plus you have this. This is with respect to T2. This will be 0 or this will be 1, right? So you have, it's not that. So it's lambda if it is, what is it? If T2 is greater than T1, right? If T1 is greater than T2, it will be lambda. So can't I write it like this? If T1 is greater than T2, this will be 1. Otherwise, it will be 0, right? So what will be RYY T1 comma T2? Anybody? So look at there. You need to take the derivative with respect to. What is this is going to be lambda squared plus. What is the derivative of this function with respect to T1? You've never seen anything? If I take the derivative, what do you get? So lambda delta of T1 minus T2. What is the moral of this story? Look at the output. Mean is a constant. Autocorrelation depends on. So we have generated a process which is not Whiteson stationary, but at the input, but at the output it is Whiteson. There is no contradiction. Previous theorem said Whiteson stationary generates Whiteson stationary. Here we have an example where process is not Whiteson stationary, but the output could be Whiteson stationary. Finally, let me just complete it by considering this case. X of t is Whiteson stationary. We want to look at the output process. So we can use, first of all, we know what is the mean. Anybody? Mean of, if the input is Whiteson stationary, its mean is? Alright, so what is the output mean in terms of? Why? Because it is here, right? Whatever is the system acts on the mean to get you the output. System is a derivative, so constant, so this is 0. And then remember, either this or this. For Whiteson stationary, this is the appropriate picture, right? So input process is Whiteson stationary. So this is what? Derivative with respect to? Or you can see it from here. We already know that the process is Whiteson stationary, right? So here, this is going to be a function of T1 minus T2, right? So this is already T1 minus T2. Look at here. This is T1 minus T2. And I'm taking the derivative. So I'm going to call tau to be T1 minus T2. So derivative with respect to T2 would be what? Right? The derivative is, so dt2 is minus, so this is the same as minus d by d tau of, you see that, right? So I can write here Rx x prime tau is minus d by d tau of Rxx tau, which is R prime of xx tau with a minus sign. Yes? Why are you having? Look here, it's also clear from here. There is a minus here, so minus tau. Or you just do it directly. Why did I put minus here? Because the process is given to be Whiteson stationary. So this is T1 minus T2. Call it tau. Then the derivative with respect to d tau will be, of course, so from here, of course, dt2 would be minus d tau, which you can see from here. So instead of dt2, I put minus d tau. So that's that. Now, we also know that the output is Whiteson stationary. So I'm going to put T1 minus T2 here, but the derivative, so this is going to be, you should be able to see that the second line is R x prime tau is what? Anybody? Look here, you take the derivative of this quantity, so what do you get? What is this? This is just a d by d tau. This was minus d by d tau. So this would be what? You can see from here also. See, put this equal to tau. No, I'm sorry. Put this equal to tau. And dt1 is d tau because dt1 is here. So this will become d tau, right? D by d tau of rxy tau. So this is d by d tau of x prime tau, or minus, you're right, r squared, right? So this is minus rxx. This is the output autocorrelation function. So what is the moral of the story? Look here. If you have an autocorrelation function, it's a double derivative with a minus sign is another autocorrelation function. You see that? It makes sense. Autocorrelation function peaks at the origin. So its derivative is 0. Second derivative is negative. So minus of the second derivative will be positive, and that will be another autocorrelation function. And I want to show you one implication of this line, then we will stop this one. So x of t is Whiteside stationary. What can we conclude about its derivative? We just did it. Look here, mean is 0. The cross correlation is depends on tau. The output autocorrelation only depends on tau also. So of course the output is also Whiteside stationary. That's not a surprise. But what we have is, look at this. Let's look at expected value of x of t, x prime of t, x prime of t plus tau. This is what we mean by Rx x prime of tau, right? T2 minus T1. So this is going to be, or we have been calling what? T1 minus T2. So let me write it. T plus tau x of t. So T1 minus T2 is Rxx prime tau, but this is d by d tau of here Rxx prime tau is minus Rxx tau. So this is minus Rxx prime tau, right? I just wrote this. We had it here. Rxx prime tau is minus the derivative of the autocorrelation function. Yes? Now look here. I want to put this just by symbolically. What will be this? What should I do on the right side? Anybody? I put minus tau here. What should I do here? So what will I get? Minus d by right? This minus minus becomes. So what do you get? Anybody? What is Rxx minus tau? Anybody? No, I mean, if the process is real, Rxx, what is the property on Rxx? Rxx tau minus tau, how is it related to Rxx tau? Anybody? Right. So this is always true. So if the process is real, you don't have a conjugate. So let's say this is a real process, real and Whiteside stationary. then you see this is the same as this, right? So what if I put a minus here? Look at here. If I put a minus here, I put, this is gone, this here minus. But look at this, this is the same as this, right? So you get this to be Rx x prime tau. These two are the, right? So let me bring it to one side. So I get Rx x prime tau plus Rx x prime minus tau equal to 0, right? Why? You seem to have lost. Conjugate is not there because I am putting a real process. If it is a real process, this is gone. Then this is then if you add, if you subtract from, these two are the same. Look at the right side. This and this are the same, right? So this and this are the same. So if I bring it to one side, you get 0, right? So far, there is nothing, everything is good. So now you put tau equal to 0. Hello? Put tau equal to 0. What can you conclude? In this expression, you put tau equal to 0. What do you conclude? Rxx. So what do you conclude about Rx x prime 0? Right? But this is the same as what? Expected value of, you put tau equal to 0. Look at here. Where did this come from? So I'm going to put tau equal to, you are not paying it, there should be one prime here, right? X prime t1 minus t2, that's how I got this. So this is expected value of x of t, x prime t. So you remember this condition for two random variables? When do you say to expected value of xy equal to 0, what do you call those? Independent, you should be out of this class. What is it? Orthogonal, right? This is like expected. So we say so what we have just showed is that if x of t is a Whiteson stationary process, then for any t, x of t is orthogonal to x prime t, or the correlation between, what is the mean of x prime t? Because x of t is Whiteson stationary. So what is the covariance between x of t and x prime t? These two random variables. Anybody? Covariance is what? This minus the product of the means, right? That's a 0 also. All right, so that is true. Now look at what happens. Suppose the original process was Gaussian. Then what happens? So this is Gaussian. Derivative is a linear operation, right? So derivative also is Gaussian. But what we have shown is this Gaussian and this Gaussian are covariance is 0. That means now what you said is true. They are independent only for that time. If you take any time instant t, if this is Gaussian, and then this is also Gaussian, or moreover for any t, they are x of t and x prime of t. These two random variables are independent. I am not saying the process is independent. So we will use this next time to show, we can use this to sometimes to show interesting results. So I showed you a lot of stuff. So we looked at the derivative process and showed you that if it is Whiteson stationary, it is Whiteson stationary. But And we also took a process which was not Whitson stationary, showed that if you pass it through a particular linear system, you can make it Whitson stationary sometimes. Example was Poisson, right?